First of all, let me thank the organizers for giving me an opportunity to take part in the fest. And Spenta Fest is one of my old and very dear friends. The first time I met him was in if I remember correctly, 1986, at one of the spring schools or summer schools in ICTP. Although we were, both are from IIT Kanpur, but there was I think the difference of about 2-3 years. So we had no overlap in IIT Kanpur. So the first time I met him in Trieste, and I was immediately struck by his single-mindedness in, absolute determination to raise the level of his own research, as well as, more importantly, the level of Indian science. That was his passion. And we used to have long discussions in ICTP. In fact, Spenta used to come almost every year. From 86 onwards, I remember I would meet him almost every year in ICTP, and many times I would come to Tata Institute, and we used to have this long discussions. I should also say, this point has been, of course, stressed by many of the speakers yesterday and today, but Spenta's, ambitions were not restricted to just developing science in India, but he was, being a left-leaning person, he obviously was internationalist, and he was also interested in developing science everywhere in the developing countries. So that was also one of the topics we used to discuss very vigorously. And indeed, as again people have mentioned already, starting from 80s, already by 90s, I say TIFR had become one of the leading research institutes in string theory. So this is, I think, to a great extent due to Spenta's works. Okay. Now, this talk is not directly related to, Spenta's line of research. It will be going back to the old world sheet techniques in string theory. Okay. Anyway, so this is so the title is Real Topological String Amplitudes. So real topological string, this is a kind of, this has been developed by Walker in 2009, 2008, and onwards. So I will describe what Walker's string is. And this work was done in collaboration with Niccolo Piazzalunga, who was a student of Alessandro Tanzini, in Sissa. Okay, this recently came out this summer. So this is the outline, motivation and statement of the question. Then I will just state the results and a very brief summary of the method, and finally conclusions and questions. Okay, so first of all, let's start from the type 2, the standard topological string, which was developed by BCOV, Bashasky, Chakoty, Ogur, and Wafa, in a very beautiful paper in '93. And the basic observation was the following, that if you consider type 2 compactification on a Calabi-Yau space, the Calabi-Yau space, the CFT of the Calabi-Yau space is described by an n equal to 2 superconformal plane with a definite central charge, C equal to 9. This algebra has these generators, the Virasoro generator T, the 2, because n equal to 2, the 2 supercurrents, G plus minus, and a U1 current, G. Now, what they did was to go through this procedure of topological twisting, whereby one defines a modified stress tensor, which is T plus, okay, there's a missing half factor, T plus or minus a half dj. The important property of this, important consequence of this twisting is the following, that the dimensions get shifted because of this extra U1 current in the modified stress tensor. So as a result, G plus becomes dimension 1 and G minus becomes dimension 2. If you had changed the sign here, then this of course changes the sign. These are called the two different types of twisting. So the result of, because the fact that G plus is dimension 1, you can define an operator, you can define an integral of G plus over a contour, and in the topological theory, one treats this operator as the BRST operator, topological BRST operator. And furthermore, and this is also a very important fact, that when you look at the superconformal algebra, of the details of the superconformal algebra, you find that Q, this Q topological of the acting on the G minus, is in fact T hat. This is quite important for the whole procedure to work. Now, the physical states are defined to be in the Q topological cohomology, which basically means that the physical states are annihilated by, the topological states are annihilated by this Q, and two states which differ by an exact state are identified. So this is the Q cohomology. Just to recall, how one sets up in the usual, say, bosonic string, not the topological version, just the usual bosonic string, how one sets up the string perturbation theory on higher genus surfaces. Okay, in the usual BRS string, bosonic string, once you go through the conformal gauge fixing, you have the BC ghost system. B has dimension 2, and C has dimension -1. And the string BRST operator, this is not the same as the topological Q that I mentioned before. The string BRST operator has the important property that the Q acting on B is equal to T. This is to be compared with this equation here, QG minus is T hat. So in some sense, G minus plays the role of B. B goes in the bosonic string. Okay. So this fact allows us to define amplitudes on a Riemann surface of higher genus, and very schematically, the form looks like the following. On a genus G surface, the moduli space of the genus G Riemann surfaces is 3G minus 3 complex. So one defines this measure, which is simply the Beltrami differentials mu, which correspond to infinitesimal deformation along the moduli space, folded with the B, and inserts 3G minus 3 of them, and that's exactly what is needed because of the zero modes of the B. The number of zero modes of B is precisely 3G minus 3. Now, this definition should make sense. In order for that to happen, the Q exact states must decouple, right? That's one of the consistency conditions for this to make sense. And indeed, if you insert a Q exact operator here, then if you deform the Q, since the Q annihilates all the physical vertex operators, then the only place where the Q acts is on B, but Q acting on B gives you T, and therefore it gives a total derivative in the moduli space. This is the way the BRS exact states decouple in the perturbation. So this was a push. So one can now define the topological partition function. This is what BCOV did. You have the FG, the genus G partition function, which is simply defined by the function path integral over all the fields being just the Calabi-Yau fields, the n equal to 2 superconformal field theory fields. There are no ghosts in this system. It's just the Calabi-Yau, the fields which describe the Calabi-Yau, the superspectral version. And you have this measure. You have 3G minus 3 Beltrami differentials. They are folded with a G minus, and this again ensures, at least in the, so now because of that relation that I mentioned before, this relation, QG minus equal to T hat, if you insert a Q exact operator, now I mean the topological Q exact operator, then once again by deforming the contour, this Q will act on the G minus, which will convert it into T hat. So it will give you a total derivative. But however, in this case, the answer is not 0. It turns out the total derivative terms, there are some boundary contributions. And that gives you this famous holomorphic anomaly equations. And the important point of this holomorphic anomaly equations, I'm not writing down the explicit form of that, because I won't be needing it, is that it is recursive, meaning the boundary contributions are expressed again in terms of the FG of the lower genus, lower Gs. So these are recursive. Now, so the question that was, how much time? So first, immediately the question after the BCOV immediately the question arose, is there, does this FG compute any physical string amplitude? Right? Because FG was just a construction, a topological, twisted construction. Does it have anything to do, for example, with the effective action terms in low energy supergravity? That was the immediate question. And the answer to that question was also appeared in BCOV, and one of the papers we wrote, AGNT, Antonia, this Gawa, myself, and Taylor in '93. And the result was that it actually computes, it's an F term, and it computes a coupling of the terms of the type W squared to the G, where W is a chiral wide superfield, and its superfield expansion is something of this type, where the lowest component is a graviphoton anti-self-dual field strength of the graviphoton, and theta squared term contains a Riemann tensor, anti-self-dual part of the Riemann tensor, and of course the other terms. So in particular, if you integrate the superspace variables, this gives you one of the terms that you get is R squared times T squared to the power of 3. And indeed, we showed that when you compute the amplitude, when you compute this amplitude, after a long calculation, it turns out that because in the full string theory, it's not just the Calabi-Yau. You have the ghost system, you have the super ghost system, you have the Minkowski part, R4 part, and its super partners. So there are a lot of other fields, and it turns out that all of them cancel, and what is left over is just the Calabi-Yau part, and that too in the twisted version. So that way you reproduce the. Since after that, there's also this work, again, another paper that we wrote in '95, where we constructed the heterotic dual of this theory. In heterotic dual, all these FGs already appear at genus 1, and they correctly reproduce the conifold singularity structure, which is governed by C equal to 1 string. And this work gave rise to Schwinger-like formula, which was a key ingredient in the Gopal-Kumar Vafa works. Of course, this has other applications, black hole physics. You have also this interesting result from the Nekrasov, the four-dimensional n equal to 2 Yang-Mills partition function, exact partition functions, where this epsilon plus parameter of the Nekrasov deformation is identified with the graviphoton. Okay. Now, that was all. All this was n equal to 2. The space-time n equal to 2 theories. The next question was, is there any possibility to define a topological string in n equal to 1 theory, which means 4 supercharges? And indeed, already in BCOV, in '93 paper, they also had a discussion of open string. Open string, of course, open string on a Calabi-Yau space, of course, give you 4 supercharges. We also, in another paper in '96, we tried to do this in heterotic string. And in that case, if you consider such a term, which is W squared to the G, where W is the chiral gauge superfield, with its lowest component being the gaugino, and the theta component being F, the field strength, again, anti-cellular field strength, this is the chiral gaugino. Then you find that this again gives you a topological, but it's of course semi-topological, because in heterotic theory, only left movers has supersymmetry, whereas right movers is bosonic. So this gives you a semi-topological theory. And of course, it's not, it turned out that it's not very satisfactory. When you look at the holomorphic anomaly equations, you do get boundary terms, but the structure of the equations is extremely complicated, and they, in particular, do not close on FGs. There are new couplings which enter in the recursive equations. So not much could be done with that. So for a long time, I thought that for 4 supercharged theory, there would be no really nice topological string. However, this Walters paper in 2009, constructed a topological string for 4 supercharges, and this was with the type 1 like theories. That is surfaces, Riemann surfaces with boundaries and cross caps, unoriented surfaces. And the main idea here in this procedure, what they do is that the R4, Lorentz group is essentially broken to R2 cross R2. It's essentially what is left over is simply the two-dimensional knowledge. In any case, I mean, as we'll see later. So, I mean, what I'm saying is that the fact that we couldn't find some nice topological theory in 4D, 4D compactifications was kind of avoided by going to two-dimensional. Okay, so, the precise structure is that you have the internal theory is a Calabi-Yau CFT with the D-branes and orientifold planes wrapped on a Lagrangian submanifold. And this Calabi-Yau admits an anti-analytic involution whose fixed point set is actually this Lagrangian submanifold. So that's the basic construction of all that. And holomorphic anomaly equations are similar to the type 2 case, except there are some additional terms. But more importantly, they close on this, I just call it f hat g, to distinguish from the fg of the closed string. So these holomorphic anomaly equations close on it, f hat g. That's a nice feature. So when this paper came, I was wondering what would be the physical string description of that. And I'll finally be, finally be, I mean, in this collaboration with Nicolo and Alessandro, we addressed this issue. And so that was the main question that we wanted to ask. What is the physical string realization of f hat g? Or equivalently, what does f hat g compute, the low energy? So, these are the results. I'll just state the results first. So the 2A theory that so we start from a 2A theory on R4 cross CY Calabi-Yau space. And this Calabi-Yau space, as I mentioned before, is not an arbitrary Calabi-Yau space. It's a special Calabi-Yau space which admits an anti-analytic involution, G, let me call it G, with a fixed point being a submanifold being a Lagrange, three-dimensional. Now you start from this 2A and quotient it by the orientifold action. Omega is the worldsheet parity, and also together with omega you simultaneously apply a G hat operator, Z2 G hat, and this G hat is a product of two actions. One is this involution acting on the Calabi-Yau, and the other is H, which acts as a parity transmission on R2. So in other words, R4 is split into R2 cross R2, and this H is acting as a Z2 orbifold on this R. So as a result, what you are left with is just a R2 Poincare symmetry. Now, okay, this results in a O4 D4. So this results in a O4 D4 plane wrapped on the first R2 and a Lagrangian and the G fixed Lagrangian submanifold. Now, equivalently, one can think of this as a type 1 compactifier on R2 cross Calabi-Yau, and again, this special Calabi-Yau, and do 5 T dualities, where 2 of the T dualities acts on this R2, and other 3 T dualities acts on directions transversal to the Lagrangian. So as a result, you see O9, D9 becomes O4. Now, what the claim is that the non-trivial part of the Walker topological string partition function, i.e., you remove the purely closed-oriented part. So what it means is that we include only the surfaces with boundaries and or crosscaps, but not closed-oriented. That part computes. I should mention, of course, this action will reduce the supersymmetry to 4 supercharges, so 2 chiral and 2 antichiral. And this is the 2 chiral thetas. In the originally we had 4 chiral thetas. Now it's only 2 chiral thetas. And this is the F term. So our claim is that this F hat G is a coupling of this the superfield, I call it W parallel to the power of G prime, where G prime, where chi is the Euler number of the Riemann surface with the boundaries and crosscaps. I call it sigma G HC, where G is the genus, H is the number of boundaries, C is the cross caps, number of cross caps. So, and chi is the Euler characteristic of this surface, and G prime is defined as chi equal to 1 minus G prime. G prime has the interpretation that you see you can always go to a double cover of this surface, double cover, which is a closed oriented surface, and that surface has a genus G prime. So this is the relation between the two. And what is W parallel? W parallel is again the same as, you start with the same original superfield, the wild superfield, but now you restrict to only the 2 thetas. You remove the 2 thetas which are broken by this orientifold action, and the T parallel and R parallel are the orientifold invariant graviphoton and Riemann tensors. Again, anti-Seppiel graviphoton Riemann tensors. So the amplitude that coupling in terms of the component fields is contains, among other things, a term like a single Riemann tensor and T to the power of G prime. And again, these are not arbitrary components. These are the ones which are orientifold invariant. Now, 4 minutes. So I just give a very brief summary of the method, and this is the main crucial point here, the way it works. Now, the vertex operator for the graviphoton will in general be of in the factorized form. There will be a left moving part and there will be right moving part. Now, the internal part of the internal, meaning Calabi-Yau part of the vertex operator is simply exponential e to the power of I root 3 by 2h, where h is the bosonization of the U1 current of the n equal to 2 superconformal algebra. There is a U1 current. H is simply the bosonization of the U1 current. So in other words, the U1 current is simply a derivative of h, d of h. So this vertex operator is very simple. The internal part is very, very simple and universal. Okay? It's simply e to the I root 3 by 2h, and right movers is e to the minus I root 3 by 2 h tilde. H tilde is the bosonization of the right moving U1 current. And notice the sign difference, and that is because we are starting with a type 2a. If it was type 2b, it should be the same sign, because you'll have the same DSO projection. So these are the opposite signs here. Okay, what we are supposed to do is to insert G prime minus 1 of such vertices. But when you go to the double cover, sigma G prime, so that the original surface is sigma G prime quotiented by this involution, then one can use the standard image trick to compute these amplitudes, so that if you consider a vertex operator V of the graviphoton at a point P in the original surface, then that can be expressed in the double cover by using image trick as the left moving part of the vertex operator, which means this part, sitting at the point P, and the right moving part, VR hat, is sitting at the image point. P bar is the image point of P, where by hat I mean that you need to also apply the involution operator on that. Okay? You can see from the previous, the discussion of how the involution acts, that involution takes h tilde to minus h tilde. That's one of the involution. That involution which I mentioned, G and H and so on, they take the h tilde to minus h tilde. So as a result, you see that what you find is that this is the graviphoton vertex operator becomes 2 identical spin fields at the point P and P bar. So notice that all the signs are the same. Okay? And that's exactly the starting point for the type 2 calculation. So here what you have is now just the left moving part of the type 2 string calculation. You don't have left and right movers both, only left movers, but from the left moving sector, you have exactly 2G prime minus 2 graviphoton vertices. And so the entire calculation goes through exactly like in type 2, and this is the main reason why we can show that it exactly becomes it. Again, there is a complete cancellation of all the other fields, R2 cross R2 fields, the ghost systems, BC beta gamma ghost system, everything cancels out, and what you're left with is just a twisted internal theory, which is what Walter's result. There is just one little point I should mention, that since here now I mean, as opposed to type 2 case, in type 2 case, you have the integral over 2g prime minus 2, right? Because there were 2g prime minus 2 graviphoton vertices, and you have to integrate their positions. In this case, however, there are only g prime minus 1 graviphoton vertices, only the g prime minus 1 integrals are there. So instead of getting a dit in tau square factor, so instead of having determinant of im tau square factor, which appears in the type 2 case, you get only dit im tau factor. But that's exactly what is needed for the open string that we are discussing, because recall that we have the D branes and the orientifold planes are wrapping on only this R2, right? So what that means is that, for example, suppose you're looking at a boundary, these directions are Neumann, these directions are Dirichlet. Okay. So when you compute the determinant of the scalars, the bosons, the x's of the R2 and this R2, this being Neumann, you have to compute the determinant of the Laplacian restricted to the even functions, right? Because the involution for the Neumann restricts to the even functions, whereas this one restricts to the odd functions. I mean, Laplacian on the odd function. So if you take the product of that, that becomes determinant of Laplacian restricted on the even and odd functions, which means a full determinant. Okay. So the total, integral gives you, I mean, the path integral gives you determinant delta square. Okay. And that's the reason why you get dit in tau, not dit in tau square. So this exactly it cancels. This factor exactly cancels the determinant. Okay, that's so I will. I will just conclude with some open questions. So first of all, what we have identified the Walker string, Walker topological string partition function with this effective action term. Now, Walker et al. Have a conjecture regarding the conifold singularity structure of this topological partition function. It's more complicated than the type 2 case. In the type 2 case, the singularity structures are basically given by C equal to 1 partition function, and that when you expand in the genus by genus, they involve Bernoulli numbers. In this case, however, at least this conjecture, according to this conjecture, it involves both Bernoulli numbers and Euler numbers. So one of the questions that we wanted to ask is a natural question, of course, is that is there a dual string description where the would-be massless states are perturbatively accessible? Because conifold massless states are non-perturbative, so it's difficult to really do a direct calculation. So if one can find some dual string where these massless states are appearing perturbatively, then by a simple one-loop calculation, one should be able to get this singularity structure. I should say that I initially thought it was going to be a very easy problem, but we tried a lot of possible heterotic duals, and we have never been able to construct. I mean, every time the answer was always 0. So I don't know what's happening. It could be that there is no heterotic dual which is perturbatively realized. Perhaps it involves already some NS5 branes. I don't know. So at the moment, we are focusing on the type 1. Dual type 1 description where there are perturbatively accessible states. Where you may have D5 branes, but that's D5 branes we can at least analyze in the CFT, using CFT techniques. So this is still under investigation. So okay, I'll just stop here, and I wish Spenta happy birthday. And as I think David said, 65 is just the beginning. I'm sure now he'll have more time to concentrate on research. And I'm sure behind the scene, he'll be still guiding the Indian science.